Hey everyone, welcome to 1.1. I call this calculus or not. So what we're going to do first is let's read you your trivia question. What ice cream chain retired the flavors Bovinity Divinity, Wavy Gravy, and Makin' Whoopie Pie? The answer at the end of this episode. So what we're going to do is we're going to talk about the tangent line, and that is the line that intersects a function at a point, and I'm going to say locally. Okay, because as you know, when you talked about tangents before, we talked about them being tangents of a circle, which means they only touch the circle at one point. So now we're going to look at tangents of a function. So what we're going to do is we're going to look at here, and let's just zoom in right now. There we go. We're going to look at right here. So if I look at this tangent, this line only touches this function at this point for what we can see, right? So this would be a tangent line, but as you can see, it actually touches the graph more than once. So we're just saying just locally, this is a tangent line at this point. So it kind of intersects the graph locally at just one point. So that is a tangent line. If I move it down here, we can say this is a local secant line right in this area, right? Because a secant line touches the graph in 2 points, just like in geometry, it touches it in 2 points. So this would be a secant line because it goes in 2 spots. All right, so there you go. Let's go through that and just say that a secant line, let's see if we can kind of get this a little bit better. There we go. Perfect. A secant line is a line that intersects a function O(n) at 2 points. And that's kind of so you can find the slope. Alright, now we're also going to talk about limits. We're going to actually define them a little bit later on, but what we're going to do is a limit is something that we can get really, really close to, but we can never actually get to. It's kind of like infinity. You can keep on adding a 0 to this. I can keep on adding zeros, and we keep on getting bigger and 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 bigger. We can never actually get to infinity, right? Because you can come along and just add another 0 and add another 0 and add another 0 forever and ever. So we can never actually get to infinity, but a limit is something where it gets really close to it. If we get a large enough number, a lot of the other numbers aren't going to change that much, so we can kind of get a pretty good approximation of what's going to happen. All right, 2 big things that are really important in calculus, and we're going to show you some examples here today, are tangent line problems and area problems. Okay, tangent line problems are kind of something that's very helpful, but we don't have to worry too much about it before, because what's going to happen is we're going to do a lot of the stuff here. And area problems are something that's going to be more with integration. So this is more differentiation, this is more integration. So let's look first at the tangent line problem. Why do we need to know this tangent line type of problem? What's the important idea? Well, speed is a big part of it. Okay, so when we're talking about speed, if you think about police officers, what they could do, and what I've done here is I've drawn a graph, and there's a whole bunch of stuff here. Let's say that you would enter the tollway at this point, and they give you a timestamp, and then they say you end the tollway, you get out of the tollway at this one, they give you another timestamp, and they say, oh, your average speed was you were going this fast. And then if your average speed was faster than the posted speed limit, they could give you a ticket. They wouldn't know when you had gone faster, because you might have gone faster and slower and faster and slower, right? You might not have been average speed the entire time the car had you. You might have been going a little slow and decided to pass someone went a little bit faster. So your average speed is something that just kind of says from here to here, this is how average how fast you went. Now we want to look at tangents. We'll say, when were you going and exactly what speed? So if they said, this is your average speed was 68 and the speed limit was 65, you get a ticket. And you say, well, you don't know where I was speeding. They might want to try and fight it in court. Okay, so remember, with average speed, what we're going to do is we're going to look at this secant and define that secant line will just be the slope. Remember how to find slope is just change in y over change in x, and the change in y's are going to be this green part. Change in x is in the orange, so that would be change in y's is f of c plus delta x, right? So it's the function value. That's going to be this q value right here. It's this one. And we're going to subtract this one, f of c, right? The function at c. So we're going to take this y minus this y, okay? And then we're also going to divide that by how much did the x's change? Well, this one was c plus delta x, and we're going to subtract c, right? C plus delta x minus c, okay? And the c minus c cancel out, so we end up with the slope being f of c plus delta x minus f of x all over delta x. And if you remember from before, that's the difference quotient that we had seen in that earlier example, okay? So that is something with the tangents, and I want to give you a little example of how this works. So we're looking at this, and this is a sine curve, all right? And oops, that's not the one actually I want to look at. I want to look at this one. There we go. We're looking at this one, and we're saying here's our tangent point. So this is the slope at this individual point. It also can be called instantaneous velocity, meaning how fast were you driving at this specific instant, all right? So we could say here's our average. You could say this was your tollway part A and tollway part B. They said this was your average speed. Now what we'd want to do is the cops could also use radar. And what happens is radar is it shoots a radio wave or shoots a pulse, and it goes out to your car and comes back, and then it says, I'm going to do it again. It does it really, really fast. And that way it'll tell you how quickly you're going in a very short amount of time. It says how much distance did you travel in this very small amount of time, giving you an almost instantaneous velocity. It's not exact, but it's very, very close. So what happens is it gets closer and closer. We get those points to be closer and closer together. So instead of having them be very far apart, hours to minutes to seconds to milliseconds, we can get smaller and smaller x values, which will get us closer and closer to actual speed. All right, so let's just see that again. We can say there's our secant line in blue. As they get closer and closer and closer together, they eventually become the tangent point. But you can't find the slope at a single point without calculus. All right, so there's the first one. Now let's talk about your area problem. Area problem. So let's say you want to find out the area of an irregular shape. Not this one. We want to go back to where we were. There we go. So we're going to look at, let's say you want to find the area of this sine curve. All right, so, and we only want to find the area between 0 and 2. So we want to find this area, and there's that little piece right there that we also need to look at. So why don't we use a rectangle to approximate the area? Okay, so I have one rectangle. Is this a very good rectangle to approximate the area of this sine curve? No, not really. So what if we make it smaller? Instead of having one rectangle, what happens if I have two? So now I can kind of split the middle and say, well, this one and this one's a little bit higher and a little bit lower, so I'm closer, but they're still not very good. So if I include it to 3, or 4, or 5, or 7, or 10, or 12, the more rectangles I add in, look how much closer and closer and better my area becomes. So I only have 95. If I could keep on going to 100, 1,000, a million, a billion, we can get an infinite amount of rectangles. Maybe we can get a very good idea of the area of this underneath this curve. All right, so that's the idea for what we're doing here with limits. And I am pretty much finished, so here's the time for me to read to you your answer to your trivia question. And again, it said, what ice cream chain retired the flavors Bovinity Divinity, Wavy Gravy, Naked Whoopie Pie? And the correct answer is Ben & Jerry's. All right, good luck on section 1.1.